In Lesson 9, we have learned how to simplify a linear system to a form in which it is immediately solvable by substitution, thanks to the reduction of the augmented matrix of the system in echelon form. This method has a general validity, in the sense that it can be applied to any solvable linear system with n unknowns and m equations. We start this final lesson by introducing a method called the Cramer rule, which is alternative to the previous one, but that can be applied only when the number of equations and unknowns in the linear system coincide, that is, when the coefficient matrix of the system is square. Thanks to the fact that A is square, we can compute its determinant, and in fact is thanks to the determinant of the coefficient matrix that the Cramer rule is expressed. The theorem related to the Cramer rule is this one. So, as we have said, we consider a system with n linear equations and n unknowns. So, in the matrix form, this system will be Ax equals B, where A is a square matrix, X has n entries, and the same for the vector B. Then, if the determinant of A is non-zero, the system has a unique solution X, whose entries are written here. Xi is given by the fraction between delta I and the determinant of A, where delta I is the determinant of the matrix obtained by replacing the ith column of A with B. The proof of Cramer's rule is a little bit technical, and so we skip it and we pass immediately to an example. Let's consider this linear system that can be written in matrix form like this, with matrices A, X, and B like these ones. In order to see if we can apply the Cramer rule, we have to compute the determinant of A and check if this determinant is different than 0. We have several entries of A that are null, and so we can use the Laplace development, for example, along the first row, or the first column, or the third row. In a totally arbitrary way, I chose to apply the Laplace development along the first row. As a nice exercise, you can check that if we use the Laplace development along the first row, we obtain as a result for the determinant of A minus 13, which is different than 0, and so we can apply Cramer's rule. Remember that we need to compute the values delta 1, delta 2, and delta 3 in this case, which are given by, in the case of delta 1, the determinant of the matrix obtained by A, replacing the first column of A with the column given by the vector B. So here, as you see, I introduce the column given by the vector B, and I simply reported the two other columns of A. Now, in order to compute the determinant of this matrix, we have two choices. Either we use the Laplace development along the first row, because there is a null entry here, or the third column, because there is a null entry here. You can check that the Laplace development along the third column gives this, and the result is minus 13. Now we have to compute delta 2. In this case, we have to consider the matrix A, which has the second column replaced by the column vector B. This is exactly what I wrote here. This time I conducted the Laplace development along the first column. You can check that the result gives minus 25. Finally, let's consider delta 3. In this case, we have to replace the third column of A with the column vector B, and this is exactly what I done here. I performed again the Laplace development along the first column, and you can check that the result is minus 52. In order to find the entries of the unique solution, we have x given by delta 1 divided by the determinant of A minus 13 divided by itself, 1. Then y is delta 2 divided by the determinant of A minus 26 divided by minus 13 gives 2. And finally, z is delta 3 divided by the determinant of A minus 52 divided by minus 13 gives 4. Hence, if we come back to the initial linear system, we have that the unique solution is the vector x given by x, y, z with values 1, 2, and 4. In the next page, I compare the Cramer's rule with the Gauss reduction technique. Of course, we must obtain the same result. You know how to play with the reduction technique. The first thing that we have to do is to build the augmented matrix of the system, and then you have to reduce it in row echelon form. You can check that with this E1 transformation, you nullify the elements under 1 in the first column, and so you create 1 as the pivot of the first row. Then you go in the second row and you normalize 2 by dividing the second row by 2, and then you nullify the element below 1 in the second column with this E1 transformation here. In this way, you have created the pivot of the second row and you have finished the job. In fact, if you go back to a linear system like this, and you use the substitution bottom up, you find z equals 4, y equals 2, and x equals 1, which is exactly the same solution that we have found thanks to Cramer's rule. So the take-home message is that for systems of linear equations with equal number of unknowns and equations, the Cramer rule and the Gauss reduction method are exactly equivalent. However, keep in mind that for linear systems in which the number of equations and that of the unknowns don't match, the Cramer rule cannot be applied. Let me finish this section by saying that it is a very nice idea to mix the reduction method with the Cramer's rule when, of course, it is possible, that is, we have a square coefficient matrix, by performing E1 transformations in order to create as many null entries in A as possible. Notice that this makes sense because thanks to the property 8 of this theorem here, in which we have seen the most important properties of the determinant, we have that the determinant of a matrix is invariant with respect to A1 transformations. As always, at the end of the chapter you have a list of questions. You are strongly invited to read and try to answer to all of them, and as usual, I suggest to test each other working in group. Let's now go to page 108, in which we see an exercise dedicated to the use of Cramer's rule. The idea is to try to make the computations of the determinants as easy as possible. In order to do that, what you have to do is to apply the E1 transformations to the matrices that you will encounter. The reasons underlying this hint are two. The first is that when we apply Cramer rule in order to solve a system with a square coefficient matrix, we are just interested in determinants. The second is that E1 transformations don't change the determinant, but they reduce matrices to a form in which there are plenty of zeros, and so the computation of the determinant is much easier. Okay, let's see the solution of this exercise. We have this linear system. We build the coefficient matrix, and we notice that there are no zeros in this matrix. So if we want to compute the determinant of A in order to know if the linear system is solvable with a unique solution, that is, the determinant of A is different than 0, we can reduce the matrix A by rows using E1 transformations that don't change the determinant, and then the computation of the determinant will be much easier. So you see that if you apply this E1 transformation on the second row and this E1 transformation on the third row, you get this matrix A1 here, which has the same determinant as A. Finally, by applying this E1 transformation, we obtain a matrix A2, which is reduced by rows. Since in order to get from A to A2 we have just applied E1 transformations, the determinant of A is equal to the determinant of A2. So we can, for example, apply the Laplace development along the first column, and what we get is 2 times the determinant of this matrix here, which is very easy to compute, and we obtain 24, which is different than 0, and so the initial system is solvable with a unique solution. The computation of the determinants delta 1, delta 2, and delta 3, which appear in Cramer's rule, can be obtained similarly, in the sense that to compute delta 1 we have to remove the first column of A and replace it by the vector column B of known data. We see that we still have a matrix with all non-null entries, and so in order to compute much more easily its determinant, we can reduce this matrix by rows applying these two E1 transformation, and if you check, you obtain this matrix here, and the determination of its determinant is very easy because, again, we can compute it using the Laplace development along the first column, which has 2 zero entries, and the result that we get is minus 24. Notice now that the vector column B is repeated in the second column for delta 2 and in the third column for delta 3. We get both times two matrices without zero entries, and so in order to simplify the computation of their determinants, we can apply these E1 transformations here and here. As you can see, we obtain matrices with a column that is quite easy because there are two zero entries here, and so the determinant will be just 2 times the determinant of this matrix here for delta 2, which gives 36, and 2 times the determinant of this matrix for delta 3, and the result is 12. Finally, the unique solution of the initial system is obtained by dividing delta 1, delta 2, and delta 3 by the determinant of A, and what we obtain is x equals minus 1, y equals 3 divided by 2, and z equals 1/2. Remember that when the size of the square coefficient matrix A is large, the technique of mixing the Cramer rule with the use of E1 transformations becomes very convenient. As a final example of the power of linear algebra, let me show you this interesting exercise. This table gives the number of milligrams of vitamins A, B, and C contained in 1 gram of each of the foods F1 through F4. So for example, if you consider the column indicated here, you have that 1 gram of the food F2 contains 1 milligram of vitamin A, 3 milligrams of vitamin B, and no vitamin C. Now the exercise says a mixture is to be prepared in order to contain precisely for each gram of this mixture 14 milligrams of vitamin A, 29 milligrams of vitamin B, and 23 milligrams of vitamin C. Now the apparently weird question is, what is the greatest amount of the food F2 that can be used to prepare the mixture? As a hint to solve the exercise, notice that in order to have 14 milligrams of vitamin A, we have to write x1 plus x2 plus x3 plus x4 equals 14. Why that? Well, because there is exactly 1 milligram of vitamin A in every food. And so, if we want the sum of the food in the mixture to give 14 milligrams of vitamin A in each gram, then this is the equation that we must write. Similarly, we have to write x1 plus 3x2 plus 2x3 plus x4 equals 29. Why that? Well, because we want in the mixture 29 milligrams of vitamin B for each gram, and we know that each food will have 1, 3, 2, and 1 milligram of vitamin B to offer. We have understood the game, and so the third and last equation that we must write is 4 times x1 plus x3 plus x4 equals 23. Again, this is because we want 23 milligrams of vitamin C, and the amount of this vitamin that is offered by the foods is written here. We then notice that these equations must be satisfied simultaneously, and so we have to write a system of these equations. And these equations are linear, so we have a system of linear equations to solve. We now notice that there are 3 equations, but 4 unknowns. We know that this means that if the system is solvable, there will be an infinite amount of solutions. That is, at least we have a free parameter. Now the free parameter will affect the value of the solutions x1, x2, x3, and x4, but they must be positive because they represent the amount of food in the mixture. So, after solving the system, which is something that now you should perfectly know how to do, you have to interpret the solutions and the parameter in order to have the answer to this question. Let's see the solution to the exercise. As I told you before, you have to write this system of linear equations here and then solve it. Here I wrote the augmented matrix of the system and then the E1 transformations that you have to apply in order to reduce it in echelon form. As you see, there are 3 non-null rows, and so the rank of A and the rank of the augmented matrix is 3. Hence, the system is solvable, but the rank is 3 and there are 4 unknowns. So we have an infinite amount of solutions with one free parameter. To find these solutions, as always, we take the reduced matrix and we transform it back to a linear system, which can be easily solved by substitution, obtaining the solution here. Now notice a very important thing. These are the mathematical solutions to the linear system. But in order to find out the solutions that make sense for our specific problem, we have to interpret them. This is very important because in applied sciences, mathematics must be used as a creative tool and not as a black box that provides you with a final answer to your problem, which instead is obtained through the correct interpretation of the mathematical results obtained. In the present case, as we have said before, it doesn't make any sense to have negative proportions for the foods F1, F4. So all these values must be positive. This, of course, implies that alpha must be larger than 0, and luckily with this choice we have that both x1 and x2 are also larger than 0. However, this is not true anymore for x3 because we have a minus sign here, and so we have to impose that 3 minus 3 alpha is larger than 0. This is equivalent to say that 3 times 1 minus alpha must be larger than 0, which implies that alpha must be less than 1. However, remember that alpha must be positive, and so at the end alpha must be contained between 0 and 1. Thanks to this constraint, we can answer the question of the exercise. In fact, let's look at the expression of x2. We see that the largest amount of x2 which makes sense is when we replace here for alpha a value that approaches as much as possible 1. If we introduce exactly 1 here, we obtain this value for x2, but in this case we nullify x3, which means that we don't introduce the food F3 in the mixture. So what can we do? Well, for example, we can set alpha to be 0.99. And if we introduce this value in the expression of the solutions, we obtain these two expressions here. This means that these mixtures, which are of course equivalent, represent the mixture of foods F1 to F4, such that we have 40 milligrams of vitamin A, 29 milligrams of vitamin B, 23 milligrams of vitamin C with the largest amount of food F2. Why is this example interesting? Well, imagine that we have a great abundance of food F2 where we live, so it is intelligent to use this food instead of the other three. Or imagine that gathering the food F2 has a lower cost than all the other foods, so again we would want to maximize its presence in the mixture, right? Hence, as a final remark, notice that by using techniques of linear algebra, we have solved an interesting optimization problem.
The course of linear algebra ends here, and so it's time to draw conclusions from what we have learned. As I told you at the beginning of this course, and as we have seen with these nice applications, linear algebra, like it or not, now I hope that you like it, is present in practically every discipline of theoretical and applied science. As we have seen in Chapter 1, linear algebra begins with the brilliant idea of Grassmann, which defined an abstract vector as an entity which behaves like geometric vectors in 2 and 3 dimensions under the sum and the multiplication by a scalar. It's really hard to overestimate the importance of Grassmann's idea. In fact, it paved the way to construct modern mathematics. As an example, we have seen that mathematicians, inspired by the work of Grassmann, generalized and abstracted the properties of collinearity in 2 dimensions and coplanarity in 3 dimensions in order to obtain the concept of linear dependence and independence. In turn, the concept of linear independence mixed with that of family of generators led us to build a basis. Then the concept of basis allowed us to underline the natural role of linear maps between vector spaces. Then we have seen that we can uniquely associate to a linear map a matrix. On a final note, I really hope that all the motivations, examples, and applications that I have discussed helped you appreciate this elegant and very useful discipline of mathematics.